Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder how we can get more accurate results when studying things like percentages and proportions? Well, this new paper explores a really cool way to do just that, moving beyond old methods to get better insights. Imagine you are trying to measure things like how often people get a question right on a test, or what percentage of time they look at a certain part of a screen. These numbers are tricky because they're stuck between 0 and 1. You can't get more than 100% right, and you can't get less than 0%. This is where standard math tools, the ones that assume things can go from super negative to super positive and have a nice bell curve shape, can sometimes lead us astray, giving us not quite right answers. Think about it like trying to fit a square peg into a round hole. Traditional models that assume your data can be anywhere from negative infinity to positive infinity, and that the spread of your data is always the same, just aren't built for these bounded numbers. This means the results we get might be a bit bent out of shape, especially when lots of our answers are exactly 0 or exactly 1. But what if there is a better way? This paper dives into something called beta regression. It is like a special tool designed specifically for these kinds of percentages and proportions. The beta distribution is perfect because it is naturally squished between 0 and 1, just like our data. This means it gets the boundaries right. So the main idea here is to use this beta distribution to understand what is going on with our data instead of forcing it into a model that wasn't made for it. The researchers then explain how to actually do this using a powerful set of computer tools in R, a popular programming language for statistics. They focus on a Bayesian approach, which is a way of doing statistics that lets us update our beliefs as we see more data. They even start by showing how the usual way of analyzing data might have some problems. They use data from a study about how the fluency of an instructor affects how much students remember. Fluency here means how smoothly the instructor speaks, with good pacing and without too many ums and ahs. In the original study, they used a t-test, which is a common statistical test, and this t-test found that students remembered more from fluent instructors. But the researchers here point out that this standard test might be flawed because the data recall accuracy is a proportion. When they ran a Bayesian version of the same old model, it looked pretty similar. But when they checked the assumptions of that model, they found problems. The spread of the data wasn't consistent. This is like noticing that the simple t-test might have missed some important details. So they moved on to the beta regression. They explained that the beta distribution has two main parts, or parameters. One is like the average or central point called mu, and the other is about how spread out the data is called phi. Beta regression lets us model both of these. Now, a small catch with the standard beta distribution is that it technically doesn't like exact zeros or ones. If you have data points that are exactly 0 or 1, you have to be a bit careful. The researchers decided to temporarily remove these extreme values to fit the basic beta model, but they emphasized this isn't ideal. They then showed how to get results that are actually meaningful, not just abstract numbers. Instead of looking at complicated coefficients, they used special tools to show the predicted percentages. For instance, they found that students who watched a fluent instructor recalled about 35% of the material, while those who watched a disfluent instructor recalled about 30%. This is much easier to understand and tell a story about. Fluency seemed to boost recall by about 5 percentage points. But they also looked at the dispersion or spread of the results. And here is where it gets interesting. They found that the effect of fluency on the spread of the results was a bit uncertain. This means that while fluency might have nudged up the average recall, it also might have made the differences between students a bit more varied, or maybe not. The effects on the spread were less clear. But what about those tricky zeros and ones we had to deal with? The paper then introduces more advanced models to handle these perfectly. First, they talk about zero-inflated beta or ZIB regression. This is super useful when you have a lot of zeros in your data that aren't just random but represent something real, like someone not recalling anything at all. They found that the ZIB model fit the data better, especially capturing that bunching of results near 0. And importantly, they saw that fluency seemed to affect the probability of getting exactly 0 correct. Specifically, a disfluent instructor was linked to a higher chance of getting nothing right. This is a key insight. It suggests that fluency might not just change the amount remembered, but whether people remember anything at all. Then they introduced the 0-1 inflated beta or Vuorre model, which can handle both lots of zeros and lots of ones at the same time. This is really powerful because it acknowledges that extremes can be meaningful in themselves. Finally, they talk about something called ordered beta regression. This is a neat way to deal with data that has boundaries 0 and 1, but is still treated as a continuous scale in the middle. It is like a more streamlined version of the ZIB or ZUIB models that assumes there is an overall ordering. When they applied this ordered beta model to the data, they found similar results regarding the average performance. But the benefit of these more complex models is that they provide a more complete picture. The ordered beta model gives us a slightly clearer picture of the fluency effect. It suggests that fluent instructors probably lead to somewhat higher accuracy, but there is still some uncertainty. It is like saying, most signs point to fluency helping, but we can't be completely sure how much. They also did these things called posterior predictive checks to see how well their models actually match the real data. The more advanced model, especially the ordered beta one, did a much better job of capturing the patterns in the data compared to the old Gaussian models. This really shows the power of using models that are built for the type of data you have. So what does all this mean? The main takeaway is that when you have data that is stuck between 0 and 1, like percentages or rates, using standard models can be problematic. These new beta regression models and their variations, ZIB, ZOIB, ordered beta, are much better equipped to handle these situations. They respect the boundaries, they can model the variability, and they can even account for special cases like having lots of zeros or ones. The study showed that by using these methods, they could uncover insights that were missed by traditional approaches. For example, in the fluency study, the ZIB model revealed that instructor fluency might not just affect how much you remember, but whether you remember anything at all. This is a huge difference in interpretation. The Bayesian approach also helps here. Instead of just a yes-no answer from p-values, you get probabilities and ranges of uncertainty. This means you can say things like, there is a 95% chance the effect is positive, or we're not sure if this effect is even meaningful. This paper is a great guide for researchers who want to use these more appropriate models. It shows that with the right tools, even simple datasets can reveal deeper, more nuanced stories. It is all about choosing the right model for the data you have to get the most accurate and meaningful results. Now, what is my take on this? I think it is fantastic that researchers are pushing for better statistical tools. The limitations of older models are becoming more and more apparent, and having access to things like beta regression, especially with the clarity that the Bayesian approach and packages like BRMs offer, is a huge step forward. It makes our understanding of psychological phenomena more robust. The biggest strength here is the focus on interpretability. By showing how to get results on the original scale like percentages and using marginal effects, they make complex models accessible. The paper also does a great job of highlighting that different models are suited for different data structures, especially when dealing with those exact zeros and ones. It's not just about finding an effect, but about understanding the nature of that effect. The main limitation, as the authors mention, is that fitting these models can be more complex than just running a t-test. But the tools they showcase, like BRMs and marginal effects, really bridge that gap. Another point is the choice of prior in Bayesian analysis, which can influence results especially with small datasets. However, they wisely suggest starting with weakly informative priors, which often align well with frequentist results. The real-world implications are huge, whether it is understanding learning, decision-making, or any process that results in a proportion or rate. Using these methods can lead to more accurate conclusions. For instance, in the fluency study, realizing that fluency might influence whether someone remembers anything at all, rather than just how much, changes how we might design future interventions or interpret classroom environment. What is next? I'd love to see more research applying these models to various psychological phenomena. As the tools become more accessible, I expect we'll see a rise in studies that are better equipped to handle the complexities of human behavior. Future work could also explore how these models can be even further integrated into everyday statistical software. So, what do you think about using beta regression for psychological research? Let me know in the comments below. If you found this breakdown helpful, please give it a thumbs up, share it with your friends, and don't forget to subscribe to RUBIN'S Mind Lab for more insights into the fascinating world of the human mind. Thanks for watching, and I'll see you in the next video.